So, for today's extraordinary seminar, will be given by Yiwei Zhang from Southern University of Science and Technology.
In China. In Shenzhen, actually. Okay. Okay. Thank you very much, and hello everybody. First of all, I will be very grateful and of the invitation coming from Professor Miharam, Professor Felix, to give me the chance to speak here. And actually, I have to say that I have a very strong kind of motivation to speak here because 80 years ago I was actually a postdoc here in the first semester organized by Felix. And in that seminar was beneficial a lot. So actually now I'm not coming to IMPA, but to go back home to IMPA after 80 years. And I would say that I was beneficial a lot during that, let's say, the semester, the first semester in 2016, and because of the pandemic, so it gets so long time to go back. And nevertheless, I think I'm go back, so I'm very happy. So today I would like to talk about a topic which we call the typical periodic optimization, or people call the typical periodic optimization conjectures, or conjecture phenomenon, for an area which is called the ergodic optimization. And that is the topic I have been working for almost 10 years since the last time that I was from my PhD. And I would like to talk a little bit about the motivations and also some kind of the main kind of conjecture in this area and some kind of recent progress of these subjects. So let us start it. So to throw off my talks, I was saying something very elementary but very important things about these deterministic chaos things. So throughout my talk, I will concentrate on the chaotic dynamical systems. So basically, I will consider two types of dynamical systems. One thing is about the discrete maps. Another thing is about the semi-flow. And people treated this one as the discrete dynamical systems, and this one called the continuous dynamical systems. And for both of these things, we will be usually interested in these things which admits the chaotic behaviors, in the sense that this kind of systems has abandoned different behaviors of the trajectory. So for example, they have the periodic orbits, sensitivity orbits, recurrence orbits, etc. And a number of very famous examples in these kind of chaotic dynamical systems can be listed as these three, at least these very canonical examples. So the first of all, the people are called these uniformly hyperbolic systems. In the other sense, the most simple case would be the Arnold-Katz map, in the sense of the two-dimensional torus, the linear one. And you can see here, you have this kind of, you can decompose the space into like, expanding and contracting direction uniformly. So in our Chinese systems, we call this is a little bit like a noodle maker, sort of. We call the ramen system. So I don't know, in Poland, they do have something like you have the ramen system, you have like these noodle, Chinese noodle things.
We do have those, yeah.
No, I mean the Chinese type of noodles.
Yeah.
Okay, we're using like this kind of a bunch of looking like this way. We call this a ramen, but yeah. And this is sort of like the things we have the expanding and the contraction. And another type, I think most of the people in dynamical systems are learning this one even before this one, is that we call the logistic family. And then you can take this family, from R to be 0 to 4. And in particularly, we have this R bigger than which we call the Feigenbaum parameter, then it admits some kind of the chaotic behavior in the sense of that you have lots of periodic things. And these two things are similar, but I have to say, although this map is sort of like a one-dimensional, it's the dynamic behaviors maybe sometimes is even complicated than that one, because you have the critical points, the existence of critical points. So it is a uniformly expanding. It's not hyperbolic. It's only one-dimensional. It's expanding. But it's expanding in a non-uniformly way. So sometimes it's not you cannot get to the uniformly control of these expanding factors. So this is another type. And of course, in the continuous section, continuous setting, we usually have the Lorentz attractor things. You have this very famous, like the butterfly looks like attractor. And you know that this is a three-dimensional ordinary differential equations, and you have some similarities. And people call this is singular hyperbolic systems. So to throw off my talk, I think I will using these three examples as a very canonical example to my studies on the ergodic optimization areas. Okay. So Next, I would say that I have to say a little bit more words about what's the sensitivity of the initial conditions. So people say this is a sensitivity to the initial condition, which means that no matter how originally you are, in these systems, you cannot predict it in the future, in the sense that this will be sometimes very nearby, sometimes very far away from each other. And this kind of phenomenon is observed by the very early back to Poincaré, or even Birkhoff, or even the computer scientist Turing, and then will be very mathematically clarified by Lee and York in 1970s, which I think they have a famous paper called periodic 3 implies chaos, and they can have a very concrete definition of what we really mean of chaoticity. So, due to this kind of the chaoticity behavior, then instead of this give us more difficulties to understanding a single orbit of these chaotic systems, because in the computer simulations you always have numerical errors, and then due to this chaoticity, then the trajectory or the orbits of what you observe in the computer might be totally different from the orbit what you want to target it for. Therefore, although the system is deterministic, we have to treat it the kind of the dynamics behaviors, or we want to study the dynamical behaviors in a much more probabilistic way. And this will be coming to the emergence of which people call the ergodic theory, which is follow the idea coming from probability. So instead of thinking just the dynamical itself, or just the one single orbit, the people tries to study about the invariant measures, which means that this one, in the discrete set, this would be the same as their pre-image, and then the measure is the same, or in the continuous set, because the continuous set is always invertible, so this means that this measure does not change under the evolution of the dynamics. And then also, we can say that this measure can be ergodic, which means that this is indecomposable. So we have the ergodic and the invariant measures. And then a first natural question is that, of course, if you're giving your dynamical systems whether such kind of measure exists or not, and there is a very general theorem called the Kragoff and Brunov theorem, which guarantees that once the map is continuous on a compact manifold or compact space, then such kind of measure is always, such kind of invariant measure is always exist. And then due to the ergodic decomposition theory, you can also choose an ergodic measure. So therefore, for such kind of systems, you always have a continuous and ergodic measure. And in fact, the people later on realized that if you want to quantify the chaoticity quantitatively, it is indeed corresponding to see the abundance of how abundant, or how to say that, this invariant measure or ergodic measure, how the abundance behavior of these things is a very nice behavior to quantitatively quantify the chaoticity of the system. So then I think this merged to the, which they call the statistical law, or this kind of ergodic theory things. So instead of we just thinking about our previous dynamic systems topologically, we're thinking them as a measure preserving system. And then, instead of, we have these triples. So we have the dynamics, we have the space, we have measure. And then, other than that, we are proposed a physical observation of physical potential, which is F. And thinking about a a process or sequence of random variables, associated with this one. So you can see that each of the stochastic process or this sequence of random variables was driven by the deterministic action of the dynamical system. And then the people are, instead of asking what orbit, they're asking what's kind of the statistical law of this, this sequence of random variables, or, and for example, whether the law of large numbers exists, central limit theory exists, law of iterative law exists, large deviation exists, etc. So basically, you can investigate the mu-typical behaviors of, the mu-typical behaviors of this stochastical process, ROE. And you have to keep in mind that although the measure is invariant, so therefore this sequence or this process is sort of like a stationary process. But it is driven by the deterministic action of that. So therefore, this kind of sequence or process will never be independent in the sense of probabilistic words. Therefore, it's indeed the dynamic behaviors to determine how dependent of this sequence are related. And that is exactly like a very quantitative version of how the chaoticity plays roles in. Therefore, the level of this dependence of this stochastic process are indeed quantified by the level of the chaoticity. So, I mean, especially if your system are more hyperbolic, then it means more dispersive, and then it means more sort of asymptotically independent. Okay, so a very simple example, which I have to say very basic, and I think everybody knows, is called the Markov average theory. And in a more kind of probabilistic words, it's just saying this is sort of like the law of the strong law of large numbers. So it's just saying that if the mu is invariant and ergodic, and if the potential is sort of like well behaved, like in L1 mu, then the space average is equal to the time average, which means that this one is satisfies the strong law of large numbers for mu almost everywhere. And in other words, that for this particular system, this mu typical behaviors, these x attributed are uniformly asymptotic behaviors. So here we do not assume any sort of like kind of hyperbolicity or even like this kind of more strong chaoticity behaviors. And this theorem says that even we do not have this one, the law of large numbers seems to be very simple to satisfy. And but for the further, let's say, more kind of refined stochastic law, say for example central limit theory or even law of large numbers, I think we definitely need to see this more. So therefore, from this point of view, we can see that the chaoticities indeed play roles, that the stationary law indeed have ranking differently. So some stationary law, for example, the law of large numbers, are much more easy to satisfy, and some of the law which are much more harder to satisfy. But the dependence is always too strong, and the dynamical behavior, you can ranking them differently. So this is sort of like the chaoticity of play roles. And as a dynamical system behaviors, basically you can usually treat this f to be particularly chosen as this is like the characteristic function of some set A. So therefore, this means that somehow the frequency of a point equal to the x is equal to for typical behavior is equal to the measure of this A, which is quite kind of natural. And also, you can also think about this is like the Lipschitz exponent things, and this means that you can define the Lipschitz exponent for the pointwise and also Lipschitz exponent for the measure. Okay. So nevertheless, this kind of idea, so I have to say go back. So this before it's very elementary, and now this kind of idea comes to be a very kind of important idea in study of dynamical systems, which the people are called the multifractal analysis idea. So now, instead of thinking this phase space globally, we are sort of using the potential and also this kind of different theta to try to give a decomposition of the phase space into different leaves. And you can decompose this kind of the phase space into two different types of leaves. So first of all is the irregular part, and second of is the irregular part. And for the regular part, it just means that the limit exists and is equal to theta. And you have varied the theta differently, and you got the different leaves of your phase space. And all of them are called the regular parts. And the irregular parts, it just means that the limit does not exist. So that means irregular. And using this way, you can find a disjointed union of the phase space into the regular part, disjointed union with irregular parts. And instead of sort of like you study the whole phase space dynamics, you decompose the dynamics on each of these leaves. And then once you can understand each leaves, then you can union them together, then you get back to this original dynamics. And this kind of idea is called the multifractal analysis. And once you have this multifractal analysis point of view, two natural questions are raised. So first of all, if you consider on the regular parts, then you will be asked what kind of the maximum or minimum values, if they are 10, if they do have, the theta will be, so that this regular part is not an empty set. That is quite natural and sort of like the first question you want to ask, because if you answer this question, then you know exactly what the regular part will be ranging from. And once you know the first question, then the second question is raised. It means that if you're choosing just the different kind of, if you know this one, then you know that you have a different leaves of this one. And what's kind of the specific structure of each leaf? Or what will be the common structure for each leaf? For, let's say, either specific potentials or generic. Let's say generic means that you can choose your function into certain functional space with certain regularity. You want to know what the common structure of this generic potential will be looks like. So, for example, whether what is the topological structure, and if you see the difference means, if you're doing the multi-fractal analysis, you're always interested. What will be the size of each leaf? For example, what is the Hausdorff dimension of each leaf? Because there will be only one measure, only one leaf which occupy the whole space, and each of the ergodic measures are mutually singular. So most of the leaves seems to be a fractal set, and that will be sort of like a key questions erased or arised from the theory, which the people are called this. I think this has three different kind of topics, but it's sort of mutually intersected with each other, and they call this ergodic optimization, thermodynamic formalisms, and multi-fractal analysis. So it's just like how to say? I think I can treat this just like a different side of a dice. So it's mutually related, but it's just thinking a little bit differently. And I have to say that they have a tremendous contributions coming from Felix and also Michal in this area, and particularly in the thermodynamic formalism and the multi-fractal analysis in the context of the dynamics for rational maps. All the other, I think I'm learning a lot of these things. And but today I would like to say more concentrate on this part, and I want to say a little bit. I want to say more about the relationship with the optimization parts, with the connection with these two areas. And I have to say that the optimization would be more concentrated on the boundary of these two slides, and the thermodynamic formalism will be thinking about more like each slides, and the multi-fractal analysis more thinking about the fractal dimension things. So, okay, so let's go back. So now I'm talking about a bit more about these basic settings for the area called optimization. So as the people say that this kind of topic is a combination of the ergodic theory and optimization theory. So we must do some optimization. So, I mean, basically, we just, as I said before, we're usually thinking about a topological dynamical system in the sense that we have a continuous map, a self-continuous map on a compact metric space. And then we can think about another potential which makes this x to r. So usually we're assuming this is to be continuous, but you can weaken this into semi-continuous, say for example. And then the people are interested to do some optimization, and the optimization here is that we are trying to do some kind of optimization over here. So we are sort of like selecting or treating all the invariant measures preserved by the original dynamical system T. And then we are thinking about to take the integral of each measures, invariant probability and Boolean measures, and then we are thinking about what kind of the superior. So this is an optimization of appears. What's the superior will be looks like? So this value we call the ergodic superior. And I think due to the Birkhoff average theorem, a variance of Birkhoff average theorem, you can also treat it this one. This is a space average optimization. This is space kind of superior to the topological spectrum, to the topological optimization parts, in the sense of that you are thinking about any points, and you are thinking about the Birkhoff average of this one. Sometimes the average does not exist, so you can take the lim sup, and you are thinking about what will be the maximum lim sup of this Birkhoff average looks like. So an important application, I think previously or in the very early stage to study about this problem is that instead of you are thinking about a frequency, you are thinking about what will be the maximum frequency of a point. And instead of you are thinking about the Lyapunov exponent, you are thinking about what is the maximum point by the Lyapunov exponent. And if so, what kind of points will be obtained for that one? If so, what kind of measure would be? So that would be like the natural question I raised in the area of optimization, ergodic optimization. And if you think about it in like a statistical mechanics way, you can think about this is your system and this is your potential, and you can think about the measure would be like some kind of a state, and then the optimization, ergodic optimization, you can interpret it as the maximum potential energy for the system. So in the energy level point of view, this is exactly like which kind of state. If you're given a potential, you maximize the potential energy. So this is another like a statistical mechanics interpretation. Okay. So nevertheless, I think now once you have this setting, then we are interested in which kind of a measure mu belongs to these invariant sets, so that this one attend this maximizing things. And graphically, you know that this for this topological dynamic systems, this MT is usually a compact and a convex. Polytop in the sense of we can start topology. So you can just thinking about what the measure is like. It's sort of like an infinitely dimensional linear programming problem. So you are thinking about which kind of the measure which attend the boundary of this one. And due to the compactness argument, and also the f is up semi-continuous, for example, this integral operator is usually continuous. So therefore, the existence of the maximizing measure or f maximizing measure always guaranteed. However, we cannot guarantee the uniqueness, because a very simple example is that you can treat this f to be a constant function. Then all the invariant measure is the maximizing measure. But you can think about that, however, but if you interpreted the problem into linear programming, you can think, although I cannot get it for all the potentials, all the f's, it must be true for generic reasons. This is a generic uniqueness. Because if this is not generic, you can see that this is somehow, you have to be maximizing in a phase of this polytop. And this is definitely not a very generic behavior. So therefore, in the very early stage, and Jenkins in his survey and also others has already proved that although we cannot guarantee the arbitrary uniqueness for all functions, we can know that we can, generically speaking, generic in the sense of that if the function space is it can be continuously and densely embedded into the continuous function, then the maximized measure is unique. So therefore, we can get existence and unique, generically unique things. So therefore, the optimization area, the ergodic optimization problem is well defined. Okay. And I have to say that, compared to thermodynamic formalisms or multi-fractal analysis, which appears in, let's say, 1960s or even 1970s, late of 1960s or 1970s, the optimization theorem seems to be slightly later, which I think, is coming from different areas, And one interesting phenomena actually for ergodic optimization is that these kind of things has a very nice dictionary between the optimization and also the people are called the weak KM theory developed by Arabic Fatih, or in the Hamiltonian systems this is called the Arbitrary mother theory somehow. And I think it's a very nice dictionary between these two areas. I just list all of them and try to slightly expand a little bit more. So you can see that from the dynamical systems and energy point of view, the characterizations of principles or operations or dualities, you have a very nice kind of dictionary. So somehow you can treat this kind of guy. It's just like a weak KM version, but not for Lagrangians, but for the differentiable dynamical systems, for smooth ergodic theory. And I think what I would like to talk about, which we call the TPO, or the typical periodic optimization, is exactly the kind of this Hunt-Ott meta conjecture. And you have a correspondence to this Mania conjecture. So therefore, in order to understand about this conjecture, I would like to say a few words about this Mania conjecture, so that let the people to understanding a little bit better carefully. And also later I will say that to dealing with this Hunt-Ott conjecture, you have a very powerful tool which we call the Lax operator, and it has a strong kind of connection with the chance operator later on. And it also has a similar thing which we call the Lux-Omerator semigroup. And you can see that and here you have some kind of the very famous things about the velocity solutions for Hamilton-Jacobi equation. And here we have some sub-action which coming from the manual lemma, which is also corresponding. So so therefore I would like to spend like let's say a few minutes to slightly talk about this weak KM theory. So the weak KM theory, and I'm definitely not the expert about that, but I just say very briefly. So the weak KM theory, they are thinking about the Lagrangian things. So basically you have a kind of a tangent bundle of the Riemann sphere, and then you have like a tangent bundle, and then you can define a Lagrangian. So from this, this tangent bundle to the R. So this is like a potential. And then the classical the very, canonical choices for the Lagrangian is the classical mechanical systems, which you put this as the kinetic energy, and this is like the potential energy, and this is called the Lagrangian. And the people in the weak KM theory is usually studying a special Lagrangian, which they call a Donnelly Lagrangian, in the sense that in addition to be, let this air to be an addition, a Lagrangian, it should be a Donnelly, in the sense that it satisfies these two kind of hypotheses, which is called the strong linear growth and also the strictly convexity. And for our dynamic system, this is very similar. We are also thinking about some maths. The maths can correspond to the Lagrangian. And then in our dynamic system, we not only think about the math, we think about chaotic math, or even like a hyperbolic math. So we always have another two conditions. Here is more like a compactness argument. So we need the compactness argument. And here you can treat it as the hyperbolic argument, or so this is very similar. And then what in their KM theory they are interested in is that you can define each of the Lagrangian, you can define which they call the critical value on a sort of like a loops. So you have a loop, and then you can define your Lagrangian, and then you can define that. And the people are interested in the critical value for each one, and they are interested in how to estimate the minimal among all. Sorry, I have some mistake here. Sorry, it should be this x. I don't think they have a b here. Sorry. So they're just interested about what's the minimum values of here. So what's the minimum value of here among all these loops? Okay, among all these loops, and then to determine which kind of closed loop having this one. That's fairly like an optimization problem. And the Mania has a very seminal kind of ideas to estimating this one by using some dynamical system ideas. So how does he do? So what he do is that instead of thinking about the loops, he sort of like associated a probability measure, just rewriting the question here. So just sort of like rewriting the question to define the probability measure here. And so this is just a rewriting. So then Mania defined a set of holonomical probability measure, and instead of thinking about the loops, he's just thinking about these measures. So, okay. So yes. So instead of thinking about the loops, he just try to think about this kind of measures of this mu. And then due to this, our consideration is that due to that our Lagrangian is Donnelly. So somehow you can guarantee some kind of a compactness argument. And therefore, you can prove that actually such a kind of the minimizing things is always exist. It's not inf, but it's a minimum. And then if such a measure is attended this minimal, in the Mania's words, they call this minimizing measure. Okay, so that setting is more and more like optimization things. But so far, no dynamics involved, because here you just consider about some probability measure. There's no dynamics involved. And the Mania's really interesting idea he showed is that what Mania showed is that for every minimizing measure, if it appears, it is preserved by the associated Euler Lagrangian flow. So therefore, instead of thinking all the probability measures, you're just thinking about all the measure which is preserved by the Euler Lagrangian flow, and then you think about that one. You take the minimum in these parts, and then you get this value, and then you can get this one by some Laurent transformations. So in fact, Mania proves this. The idea from Mania is that so the tries to think about the minimal critical value problem is just you thinking about a dynamics, which is called the Euler-Lagrange flow, and you're thinking all the invariant measure preserved, and then you think about the Lagrangian over this flow, what the minimal looks like, and that will be the answer of the minimal critical values. So he develops some methods. For example, he wants to know about what's the kind of support of this measure, and he defined this set to be called, which they call the mother sets. It's just the sort of like all the minimizing measure for this preserved by this Euler-Lagrange flow, and you take the union, take the closure, and this is called the mother sets. So this is a tool of the Mania says how to study this measure. And based on this kind of terminology, he proposed a relatively famous conjecture in the area of the weak KM theory. People later on called this is Mania's conjecture, which is they treated as a least action principle in the sense of the mechanics systems. What they said that now you're giving you a Donnelly Lagrangian of the class CK. You have to say here, you must be CK, and the K larger than 2. So somehow your class should be regular, very regular. And then you give this Lagrangian arbitrarily, then you take a little bit of perturbation. So you take the Lagrangian a little bit of perturbation, and you created a new Lagrangian, like you have a perturbation of your original Lagrangian. And then you denote by the CK of the potential equipped by the CK topology. And the Mania conjecture can be stated as this one. It said, for every Donnelly Lagrangian given of the class CK, there is a residue sense, there's a residue perturbation of this one, so that the mother sets of the perturbed Lagrangian is very simple in the sense is that it's either an equilibrium measure or a periodic measure. So that is what the Mania's conjecture says. And to my knowledge, I think so far the only knowing case is just for K is equal to 2. And I think it's solved by Contreras, and for the CK, which is larger than 2, is still largely unknown. Okay, so that's the Mania conjecture. And in spite of this conjecture, then we can also propose some kind of the general idea into the, as I said, you have a dictionary. So then you borrow the idea coming from the Mania conjecture to the smooth dynamical system, differentiable dynamical systems. So then the people have proposed this general problem for optimization problem. What does they say? They said now, instead of fixing Lagrangian, we're fixing a nice dynamical system. And then we fix a nice family of potentials. So, okay. And we try to understand about what's the maximizing measure for all or most of these potentials looks like. And of course, this kind of problem will be less interesting if this T has only very few invariant measures, because if this T is sort of like an irrational rotation, is uniquely ergodic, then you have only one candidate, so everything should be in. So therefore, we always need the nice seems to be sort of chaotic, or more precisely, we hope it's more hyperbolic somehow. So we in the most of the literature, the T is usually assuming to be strongly hyperbolic. Because if you have a strongly hyperbolic, you have the specification property, then you have a lot of, the periodic measure is dense, so you have a lot of kind of different types of invariant measures. So this will make this problem much more well-defined and more highly non-trivial. And it's much more like the Donnelly Lagrangian setting. And then, so in what I follow, therefore in the very beginning, I just proposed these 3 kind of hyperbolic systems. So in what I follow, I will mainly consider this T to be the uniformly expanding or uniformly hyperbolic systems, for example, like the Arnold cat map. And secondly, I have to say, philosophically, this kind of problem has a very similar behavior as the Mania conjecture, which we need to assuming high regularity of your potentials. So indeed, the regularity of the potentials are make the things quite differently. So for example, if now we are assuming this T to be uniformly expanding or uniformly hyperbolic, if we only consider about this C0 potential, the regularity is C0, then the maximizing measure is unique zero entropy weakly mixing, but fully supported. So it's sort of fully supported. So you cannot be shrinking like as a periodic measure or something. It's fully supported, generically speaking. However, if you make your how to say, like a potential more regular, say for example, more regular than the C alpha case, the Holder continuous, alpha Holder continuous, or smooth continuous. Or of course the topology are different. So this is C0 topology, this is C alpha topology. Then you will have what the people call the subordinational principle. In the sense of that they do have some kind of the existence of non-trivial mother sets, which is appropriated compact invariant sets, inside of this K, so that the support would be belongs to here. So you do have the collapse of your measures when you increase your regularity. And this cannot be observed generically in C0 functions. And that will make the behaviors much more reasonable, like a periodic measure, as what's the, so therefore it's the same kind of philosophy. That the Mania conjecture is always assuming the potential to be C2, and here we're always assuming this potential to be C1. And so other than that, in let's say the, how to say, like let's say end of the last century, and you know, the people coming from Hunt and Ott, they proposed a very interesting but non-trivial kind of nice examples. So they think about their dynamics now to be this 2x mod 1 on the torus, on one-dimensional torus, so the super simple example. And then the people, they want to test is that for certain kind of the space, like the space of the linear combination of the cosine sine, or the linear combination of the trigonometric functions. So like you have the two parameter, like alpha sine x plus beta cosine x, for example. Or I think what's the really kind of thinking is about the family, like the t is equal to 2x mod 1 on S1. And then their family, I think their family is called the g theta, and it's called the cosine 2 pi x plus theta. It's the same as the linear combination of the sine and cosine. And they call this family is a translation family of the cosine. It's a translation family of the cosine pi of this family, this one. And there's a sort of like a very important results in this direction. Firstly, they just numerically tested, and they find is that for most of the parameters, this maximizing measure is numerically observed, sort of like a periodic measure, but does not mathematically proved. And later on in 2000, I think there's a French mathematician called Derry Bush. He wrote a paper in French called "The Fish Has No Bones" in French. Somehow he proved that mathematically regularly speaking, for this particular family, that does exist. So he has a number of results actually. First of all, for there exists an open dense set here. So open and dense set here for theta, open and dense set, such that this family, the maximized measure is unique and periodic. And secondly, there exists four Lebesgue measure parameters, so that the maximized measure is unique and periodic. Thirdly, for all the thetas, this measure seems to be Sturmian. So this is for all. And finally, for all the measure which is Sturmian but not periodic, the Hausdorff dimension is 0. So we have four different results. So first of all, say topological generic, this is periodic. For probabilistic generic, this is periodic. All of them is low complexity. So remaining of them has Hausdorff 0. But this one is only for particular family of maps. It's just a linear combination of this kind of particular family. It's a finite dimensional version. So then the people say the TPO is exactly like the infinitely dimensional version of the point. So somehow the TPO is exactly like we have a more general dynamics and more general potentials, but it's infinite dimensional. And such a kind of the Bush's phenomenon still holds. So that is exactly like the TPO says. So based on this kind of results, I think in 1996, Bram Hunt, this guy, and Edward Ott proposed in their conjecture 2. They proposed this kind of conjecture later on, especially in Gyro's ICM talks. He addressed this name as the Hunt-Ott meta-conjecture. He said that what the conjecture says that for typical chaotic systems and typical parameter families of smooth functions, the most values of the parameter, the maximizing measure, is unique and supported on aperiodic orbits. So why they call the meta conjecture is, unfortunately, all these kind of colored words are not mathematically defined. So later, I think in 1990, in nonlinearity, I think there's a so Bram Hunt and I think at that time Ott and Yuan, I think he's sort of in did his PhD thesis. They proposed, which later they called the Yuan-Hunt conjecture, or Yuan-Hunt topological TPO conjecture. They tried to, mathematically formulate their original conjecture in a much more kind of concrete terms. So instead of thinking about typical chaotic systems, they think of very specific kind of systems, which is the classical, like the uniformly non-invertible experiments or the unorthodox diffeomorphisms. And instead of thinking typical parameters, I think they addressed this is a different kind of concept. They addressed this is topologically generic for Lipschitz function and the C1 function. And then the result is the same. They also conjecture that this is maximizing measure is unique and supported on periodic orbits. So this conjecture is the same philosophical, but technically speaking, they have addressed more restricted kind of systems. And the typilarity seems a little bit different. So here they have like a typical parameterized families, but here they are thinking about this, it's called topological generic in a residue sets. So somehow this conjecture seems to be much more like the Mania conjecture's favor, but by addressing this is the typilarity or genericity into the topological version. So the original one seems to be much more like a probabilistic version of generic. And yes, so and before I have to say the results, I think there's also a very interesting relations between the the optimization measure and the equilibrium states. So other than the optimization, as I said, there will be a quite relevant kind of studies about this kind of using the energy behavior. It's not only using the potential energy, but using the free energy here. So instead of maximizing just the here, the people there's an even larger group. They studied about the equilibrium state, which means that instead of maximizing just the potential energy, they maximizing the potential plus the potential energy, the kinetic energy plus the potential energy, which means that this is called the free energy things. And then they think about whether the maximizing here, they call this is equilibrium states. And usually, if you assuming some kind of some hyperbolicity in your dynamics on the compact space, you can get this function, the entropy function can be absolutely continuous. So therefore, for many systems, you can also guarantee the existence of equilibrium states. And instead of thinking about the equilibrium states, in the physics or in mathematics, they are also parameterized another kind of another temperature parameter T here. And then for each T, you can guarantee a sequence of equilibrium states, mu T. And the people will be interested in is that, what will be the accumulation point as the T goes to infinity? Because in the real world, this T is represented as the reverse temperature in the real things. So therefore, it means that what will be the happen to the T goes to infinity, or the temperature goes to 0. And the people call this is a ground state of this sequence of equilibrium states. And it is relatively easy to prove that as long as your dynamic system has a finitely dimensioned, has a finitely topological kind of entropy, then each of these grounds for the equilibrium state is a maximized measure. And actually, it's the very important maximized measure with the largest complexity. So it's the maximized measure with the largest entropy. So therefore, we can, if the maximized measure is unique, then it must be this measure. And then, once you understanding about the TPO, then you exactly know what's kind of the ground state of your equilibrium states. So therefore, I have the interpolation of this one. And to say these words a bit more, so there's another second dictionary between the thermodynamic formalisms and the ergodic optimization in terms of these words. So, for example, the thermodynamic formalism is thinking about maximizing the free energy, but the optimization is potential. We are the equilibrium, but here the ground state. Here is the standard algebra, we have the max plus algebra. Here we have the chance operator, then we have the lax operator operator. And here we have the linear, max linear. Here we have a spectrum gap. Here we have a question mark. So here, very likely, I think we have the max plus spectrum gap. And what does the max plus algebra think? Another word is called a tropical algebra. It just changes the operator to be the max plus addition to be the maximum, and the max plus multiplication to be the addition in the classical sense. So therefore, in this dictionary, in this kind of dictionary, we exactly can treat the optimization kind of problem as a tropical version of the thermodynamic formula. And you can find a lot of analogies between these forms of view. And so for example, but you have a significant differences. So therefore, I would like to. This is a very interesting kind of another very interesting kind of connection between these two fields. Okay, so let's go back to the TPO conjecture. So since then, there's a large number of the people in the community trying to prove or disprove this kind of conjecture. For example, Yuan Hunt themselves, Contreras, Lopez, and Torrance, and Boozy himself, in variety settings, Brass and Quartz and Morris or something. They have variety settings. And also, I think there's also a large group of people who tries to extend this kind of conjecture in terms of the co-cycles. For example, I think Miha also did some work towards this direction. And eventually, I think in 2015 or 2016, there's an invention paper by Contreras where there's a breakthrough by Contreras where he sort of using the eventually he proved that for uniformly expanding systems and for topological generically Lipschitz functions, the maximized measure is unique and supported on periodic orbits. And actually, I think the conclusion can hold for a little bit more stronger. So what he can prove is that, generically speaking, there exists an open dense set such that it's not only supported on a periodic orbit, but is robustly, it satisfies certain kind of rocking property. Somehow is that there exists an open dense set, so that for all the functions in this open dense set, the maximized measure is not maxed by a periodic, but robustly maximized by a periodic. And the key argument for the Contreras kind of the work is actually he has to using some intermediate steps coming from the Morris original paper, where Morris originally showed that this one is generically there exists an open dense set where this is zero entropy. And then Contreras has made some further, more refined arguments to reduce the zero entropy to be exactly final like periodic measures. However, his method seems to be not that direct to generalize to hyperbolic case. And secondly, it's obviously not that direct to generalize to the systems without uniformly expanding. So I think our team in the last few years make some improvements in spread of the Contreras type of results. First of all, I think for topological genericity, myself and also some Chinese group coming from USTC, Huang, Lian, Ma, Xu, we give a fine comprehensive answer to the Yuan Hunt conjecture in the sense of that we are not only answer the question in expanding case, but we also extended it into the comprehensive. We are answer the question for the anosov diffeomorphisms and even for the anosov flows. And not only answer for the Lipschitz functions, but we also answer for the C1 functions. So we give a comprehensive answer to the original Yuan Hunt conjecture. And secondly, I think compared to Contreras' original methods, our current method seems to be more direct in the words of Jarobuki. And he said our method sort of like bypassed the zero entropy argument coming from Morris appears in Contreras proof. And it seems like more easier to using that method to generalize to more, let's say, non-uniformly hyperbolic systems for both maps and flows. And by adapting these kind of methods, recently myself and also Oliver Jenkinson, Wen and Xu, generalized this one into a more general non-uniformly expanding systems, including intermittent maps and also called Ekman maps. And also myself and Zhang Li last year generalized this one into which they call the expanding thrust maps or the coarse expanding systems, and some number of systems. Okay. And secondly is that instead of we're thinking about the Contreras type of results for the topological genericity, we are sort of like to investigate some probabilistic genericity, and this back to my postdoctoral work with Gyro. In 1916, we first investigated the probabilistic version of the Yuan-Hunt conjecture. In the sense of that, we are thinking about, we introduced some probabilistic genericity for infinite dimensional functional space, which we call the prevalence. And then we studied about in the prevalence setting, what kind of whether the Yuan-Hunt conjecture still exists or not. But in that paper, we needed to add a very, let's say, relatively ugly or strictly assumptions. We needed to assuming the regularity of the function to be very, very regular. And in a recent paper with Jian Ding and also Zhiqiang Li in Peking University, we sort of significantly improved that regularity using some probabilistic, using some, using some methods which the people are used in the probabilistic setting for extreme value theory.
By improved, you mean you lessen the assumptions?
I enlarge about the operation
okay.
Much larger, significant. And this was published last year. And let's talk a little bit about how to prove the Yuan-Hunt conjecture. We sort of like, I think in this talk I want to say more concentrate on the topological version parts. So we can summarize the Yuan-Hunt conjecture proof into three main ingredients somehow. So first of all, I think we just asking whether this kind of, we have certain kind of the dual formalisms or rigidity things in sort of like we needed to solving like whether the Lex operator, the Lex operator operator has a fixed point. And we try to get what the people call the Mania lemma or the Mania-Guiwash lemma or Mania-Kohns-Guiwash lemma to try to find the existence of the mother sets. And this is one part. And usually this part is the most difficult part actually. One of the most difficult parts. And secondly is that we needed to define some kind of a more refined closing lemma or quantitatively closing lemma. In the sense of that, we needed to use some kind of a strong shadowing to find, so once you have the mother sets, we needed to find some kind of if the mother set has already contained the periodic orbits, we're done. Usually the mother sets do not have any periodic orbits. So then we needed to develop a certain kind of closing lemma to find some periodic orbits, which is outside the mother sets, but it has a sparse gap compared to the distance of this periodic measure to the mother sets. So somehow we need to somehow have a very good selection point. So this step, I think yes, Contreras or yes, some people call this step is called a selection process. And then once you have this, we can select a very good kind of the orbits, periodic orbits. And then once we can select this good periodic orbits, then we can do a perturbation of a distant function of this periodic orbits for the original potential, so that to make the perturbed arguments to be sort of like, no matter original one is not maximizing on the periodic orbits, after the perturbation, we can have the maximizing measure move to the periodic orbits. So this is the three kind of very close to connected steps. And in our original one, which we're dealing with the uniformly case, we can do these three steps globally, sort of no matter where, just entirely of your dynamics. But if you are doing with the non-uniformly parts, then you need to be very careful. You cannot do it globally. you have sometimes we need some hypothesis. For example, if you're doing the intermittent case, you have to split into your dynamics into two parts. One part is the neutral fixed point, one part is the remainder. And then you need to do some local version of these three parts on the remaining parts locally, so that you can do these things again. And if you are in the quality-Ekman case, we need to assume usually it's like some kind of, we need to assume, for example, we need to assume it's supposedly finite. So you again split into these steps into the orbits of the critical points and the remainder. And then you're doing some careful ways on the critical points and away from this one, and then you eventually did this kind of approach. And if you're doing with the cos, and again, and then you need to develop some kind of a method which you developed by Zhang Li, also Felix. If you're using the remaining case, you need to involve into like a visual metric things to do it, and then you have to go this visual metric go back, not only go back. You need some control of the regularity to make the space do not change too much of this changing of the metric. So once for the cos metric, you are Lipschitz function, and the original back, you are also some sort of like a Lipschitz function. So you need some control of when you change the metric things, sort of like this kind of. So this will make us to realize these three steps not only for the uniformly expanding or uniformly hyperbolic systems, but also for certain types of strong expanding but not uniformly expanding systems. For example, like intermittent case or conjecture case, also some polynomial or some expanding system maps case. Yes, and also, and of course, because here, I know that people here are doing much more like a complex dynamical systems. So we believe that currently we can do something from here. So we can do this, rational expanding system maps or this kind of stuff. And there's a very famous kind of a dictionary, another third dictionary coming from Sullivan, which they call the Sullivan's dictionary. So we believe that the current method can also propose the same thing to the geometric group theory. So for example, I think we can also discuss the similar problem in the compact Klein group or Kolmogorov hyperbolic group. And we suspected that maybe, we're not done yet, but maybe we can also state some kind of a version in the sense of here, in the sense of this, this geometric or this geometric group theory, for example, like a plane group stuff. Yes, and I have to say there's this year, there's also a relevantly even more recent works, which I probably can speak next time when I come to INPA. We are still doing, but there's a breakthrough results coming from Gao and Weishao Shen. Recently, they proposed in the archive. They can, instead of thinking about this TPO, they can investigate it about the optimization measure for real analytic circle expanding maps and proved a zero entropy argument, not for typical, but for all non-trivial real analytic potentials. Non-trivial real analytic means that it is not cohomologous to a constant. So this here is not a typical result. So these are all somehow. This is like the inverse infinitely many version of these bullshit results. And I think in the recent communication with them, I think they told me at least, or they have announced that not only for this, they can even show that this is not only having not zero entropy. They treated this like a Sturmian-like measure. So it's a very like a measure which is not Sturmian but a very light Sturmian in the infinitely many dimensional case. And they believe that using this method, maybe one can even show the genericity not for C1 topology but for C2 or CR topology, like the real version of the Mania lemma for the TPO case. But they have a very restricted things. They needed to assume in the map only one dimensional and especially real one dimensional. So they cannot do for high dimensional case. They heavily relied on this is like a one dimensional case. So this is a recent proposal by Weishao Shen and Gao Rui. And I think in a recent work, I joint work with Oliver Jenkins and Hong Wang, we now can investigate the TPO conjecture for general subshifts beyond the SFT. So for example, I think we know that this TPO is still true in the Lipschitz function for Sophic systems, S-gap maps. But you can find some example which is called coded systems, which the TPU does not host. So we're currently still investigating this direction. And we believe that using this kind of things, maybe we can see more general system for naive hyperbolicity. And another thing that recently I joined to work with Oliver Jenkins and also Xiaoran Li, and he will go to a PhD student with I think in California Tech, probably with Nikita Markolov. And we investigated these optimization things for multiple valued maps, including a system coming from David Bush, they call it anti-dynamical system. And finally, I think in a recent work with some students, with Oliver Jenkinson, we investigated Manila lemma not only for Holder potential, but for other more kind of less regular potential, for example, Dynamical potential. And then we show some interesting behaviors. And I guess that's all for my session. Thank you very much. And in particularly, okay, there's no Polish, but I think
it's on the next slide.
So. Yes, the next slide. Yes. So Felix and Ni Hao, and yes, I do appreciate it for, I learned a lot from them. And, I do hope that everybody can visit us in China in the near future. Thank you.
I have a question, but it might be very, very long. So if it's too long, tell me. So for a moment you start speaking about the probabilistic version of this. So this requires a measure on the space of
Here.
The probabilistic version. So this requires a measure on the space of functions.
Yes.
Could you tell a little bit about this measure?
Okay, so I think there is I can see a little more words like this one. So there is a well-developed theory called probabilistic. It was introduced by some function analysis people, and indeed you can treat it like here you're doing some perturbation. It's like a deterministic perturbation. So here, the topological dynamic eventually you can show here is that I just say a few words. So here we find the hyperbolic measure, the aperiodic orbits. Then you're doing a perturbation. It's like you're doing a perturbation of a distance function. You're doing a perturbation like you're doing a perturbation of G. You're doing a perturbation of the D of this. So you're actually doing a deterministic perturbation. So the key point is find this orbit. Then you're doing a distance function to this orbit. So it's a deterministic perturbation. And here, for the probabilistic version, as you said, is that we are, instead of doing a deterministic perturbation, we are doing a random perturbation. And the random is what you need to find. It's needed to be a compactly supported measure, satisfy certain property. And once you can find this measure, then you are sort of done. So you're sort of like doing a random perturbation on here. And you need to get some clever ways to find this, to define this measure so that you can do the random perturbation. So therefore, here it seems to be a little bit more difficult. No, I mean, not difficult, but more difficult than here. Because here you're just doing a very specific kind of perturbation. But here you need to do a much more kind of perturbations.
Thank you.
Can I ask a question?
Yeah.
There was a slide, the top of the slide was a nice example, Hunt, Ott, Jenkinson, and Bosch.
Yes.
A nice example. And theorem Bosch 2000. And then it is written open and full measure subset. In which sense full measure subset?
La Vega. La Vega full measure.
Okay.
La Vega full measure. It is. Well, I mean, I think it can be even more stronger because actually, Bush actually proved in his paper. He said for all the parameter here, this is Stormian, but the measure which is dominant but non-periodic measure is only has Hausdorff dimension 0. So it's indeed a Lebesgue, it's much stronger than Lebesgue 0.
It's like the map from the rotation number to the parameters. It's a double staircase, but so steep one that it takes all the irrational numbers to a set of how to dimension 0.
Yes.
Thank you.
Yes, it's much stronger than the Lebesgue 4 measure, I think.
Thank you. Thank you.
This is looking phenomenon, yes?
Yeah, this is looking phenomenon, yes. And I think there's some results even for the co-cycle setting for this kind of phenomenon. It's also true by Bush and Maris and also Ian Morris and also Gita. Yes. But so far, I think, to my understanding, the co-cycle version of this TPO are still unknown, and it was proposed by Jarobuki in his ISM talk.
There aren't any more questions, comments, Felix, you wanted to?
I just wanted a bit theory being developed by you with
Okay. Well, that's I think partially it's because I learned a lot from Impan, and also my colleagues are very good at doing work at here, and it's a result. Yes, and I think I have to say that there's still plenty of problems in this area which is unknown. So it seems like it's quite worth to spend some time to discuss a lot, especially as you are students. So I think work a lot on this co-cycle setting, which I did not presented much. And for the co-cycle setting, all these things, this question you can ask again, but most of the answer will be not known.
Let's find the speaker again.
Thank you very much. Thank you, Carol. Thank you.
Thank you. Goodbye. Thank you.
Thank you.
Bye.
Yes. Hope to see you in China.
Yeah, hope to see you.
I know that you have some not very good experience.